The first problem on the test was this one. Calculate the magnitude of the force couple F so that the resultant moment on the beam is 1.5 kilonewton meters clockwise. And the figure looks something like this. Of course, you should realize you're going to have reactions at the wall, but that's not really our concern. We're going to apply some force F as follows, such that we can not just counterbalance the moment caused by the 2 kilonewton force couple, but so that we can have a resultant. In other words, a sum of moments from all these things that come out to 1.5 kilonewton meters. Now, some dimensions that were given, for example, are 0.9 meters. And then the moment arm between the 2 kilonewton couple is 0.3 meters. And so that's all the information we need. We're not saying the sum of moments are 0. Rather, what we're saying is the sum of the moments need to come out to 1.5 kilonewton meters, but counterclockwise. Now, we usually take, clockwise, pardon me. The specification of clockwise. We usually take counterclockwise as the positive direction. So what that means is we want the sum to come out negative. You see? So it needs to come out as negative 1.5 kilonewton meters, which would be in the clockwise direction. Well, what is the sum of the moments? Well, we simply need to take the moment of these combinations of couples, right? These two couples, and probably the most logical point to pick is point B to sum moments about. It doesn't matter what point you sum moments about, you will always get the same result. It's kind of interesting. That's a feature of force couples. Anyway, so if we sum moments about point B, what would we get? Well, let's see. The 2 kilonewton load has a 0.3 meter moment arm. Notice it is counterclockwise, therefore positive. In the direction that the force F is drawn, well, it's causing a counterclockwise moment with a moment arm of 0.9 meters. Make that look like an M rather than an N. So we're going to have minus 0, well, let's put it in consistent order. So minus F times 0.9 meters, because the moment of the force couple F is a negative thing. This needs to come out to a total of negative 1.5 kilonewton meters. Sorry if I'm off the screen just a bit. But this needs to add up to negative 1.5 kilonewton meters. So notice that obviously F is going to have to be in kilonewtons for this problem, see? At least for the units to be consistent. So all we really have to do is solve for F now. So if you calculate 2 times 0.3, that's pretty easy. That's 0.6 kilonewtons. Let me bring this to this side, so plus 1.5 kilonewton meters equals, let's take this to the other side, F times 0.9 meters. And so all we have to do is divide both sides by 0.9 meters. That'll take care of the, well, I guess I forgot to write meters there, but that'll take care of all of it, and we'll have F left. So let's see, what is this? This is, 2.1 over 0.9, and those are kilonewtons. If you do the math, that comes out to 2.3 repeating kilonewtons. So there's the amount of force F that has to be applied in this direction in order to have a net or a resultant moment of 1.5 kilonewton meters counterclockwise. Students often get confused between a resultant and a reaction. Both start with R, so poorly named, but oh well. A reaction is a force that is generated as a response to something. So we don't have a reaction that we're analyzing here. Yeah, there'd be reactions at the wall, right? This wall is not going to let the beam break, at least we assume that. And so yes, there will be some reaction, but that's not what we're interested in. We're interested in the resultant. In other words, the sum of all these externally applied loads, and that sum needs to come out to this amount. So that's how you work problem 1. Problem 2 said calculate the reactions at points A and B due to the distributed load. So the beam looks something like this. It's pretty simple. We've got a pivot point on one side, we've got a roller on the other, so a simply supported beam with a distributed load that decreases linearly along the length of the beam. In fact, on this side, it's actually 15, not 1.5. It's 15 kilonewtons per meter, and 5 kilonewtons per meter on the other end, with a beam span of 8 meters. I guess I should make that go over a little farther so it's obvious I'm going from pin to roller. Okay, so you got to be careful here. It's really easy. I guess this is sort of a human factors thing. I've seen this in the test as a problem, but breaking up this distributed load into two parts is a good idea, but make sure you do it right. So what I like to do is draw on top of the distributed load so I keep myself straight. I want to see 5 kilonewtons on the other side, no problem, or 5 kilonewtons per meter. That's easy. How much is left? 10. Right? Because 5 and 10 are 15. Some of you used 15 on the left-hand side of basically a distributed load that looked like this, that was a triangle plus a uniform distribution. There's nothing wrong with breaking up this distributed load this way. Just make sure you've got the right numbers that you're using, because this will be 10 kilonewtons per meter, while this is a uniform 5 kilonewtons per meter. Okay? Now, what I did is I took these two distributions and I said, okay, what's the equivalent, or equal if you will, resultant? So let's go from, let's see, I guess it'd be nice to name the points A and B. So going from A to B, with what sort of load or resultant could I replace this distributed load? Well, let's answer the question first about the uniform load, because it's easier. What's the total load? Well, that's pretty easy. We got 5 kilonewtons per meter and we got 8 meters. It's like saying I've got, $5 per apple and I got 8 apples. Same thing, right? All you got to do is multiply 8 by 5, that's 40 of course, and that's the resultant force. That's all this force added up, right? So what are 8 fives? 40, right? So 40 kilonewtons. Where does that resultant apply itself? Well, since it's a uniform distribution, it's just at the center. So we've got 40 kilonewtons of force right here at 4 meters, right? It's in the middle of the beam. So that's the resultant of the uniform load. What do you do with the distributed load that varies, or the triangular distribution? Well, again, we need a resultant. We need a sum of all of this. And that's equivalent. You'll notice what I basically did was calculate the area of this uniform distribution. Do the same thing for the triangle. How much area have we got? Well, it's got a base of 8 meters, a height of 10 kilonewtons per meter. That's 80, but it's a triangle, so cut it in half, and guess what? We've got a resultant of 40 kilonewtons for the triangle as well as the uniform distribution. I probably should have changed the problem from this, so you'd end up with two different resultants, but anyway, that's how it wound up. Where does that resultant act? Well, it acts basically at the centroid or the balance point of the triangular distribution. So it's 1/3 of the way from this edge, or 2/3 of the way from that edge, see? So we need 1/3 of 8 meters, or in other words, 8/3 meters, or we need 2/3 of 8 meters for this other side, so that would be 16/3. Okay? So if we want to know where that 40 kilonewtons acts from the upper distribution, the triangular distribution, well, it's at 8/3 meters. Now, I think I used decimal for this. No, I left it in fraction form for the time being. And if we want the distance over here, then, as I said, 16/3. Of course, the meters go with 8/3, not the thirds in not the 3 in the denominator. Same thing with the 16/3. Okay, so you can put that in your calculator, and yeah, what would you get? 2.6, right? So 2.66, I think, for this one, and the balance there. Anyway, so 5.33. So calculate the reaction. Well, now that we've got an equivalent, an equal behavior due to the resultant, we don't really need these distributed loads anymore. If we were in strength of materials, it would matter, because we'd be interested in stress and strain, primarily shear force and the moment along the length of the beam, but we're in statics, so we don't have to worry about that yet. So we want to say, okay, if we have these two loads applied to the beam, because that's basically what we have, is two distributions put together, we're going to have an equivalent behavior. Basically, we can replace the whole distributed load on the beam with a 40 kilonewton load that acts at 8/3 of the length in meters, and a 40 kilonewton load that acts at the center of the beam. Okay? So to have the remaining distance here, whatever, it doesn't really matter. Okay? So these two point loads will have the same effect on the beam, not internally, but at the reaction points that the distributed loads have. So all we have to do now is some moments, for example, about point A, taking counterclockwise as positive, because we know it's sitting still, right? So we need enough reaction force at B to react to these two, or this distributed load, whichever way you want to think about it, and keep the beam from going down. Now, just intuitively, which side is going to have more load? Well, that side, right? This is going to be smaller because there's just less load, less distributed load over to the right and more to the left. So I would expect the force at point A to be higher than the force at B. Let's find out. Let's see if we can do the math right and make that happen. So I called this F1 and I called this one F2, just so I could make a symbolic equation, make sure I kept myself straight as I worked through a problem. So if we're summing moments about A taking counterclockwise as positive, then F1 is going to cause a negative moment. Its moment arm is, of course, L over 3. That's the way I did it. I wanted to use symbols as much as possible so I could kind of check myself along the way. So just the length, 8 meters over 3, would be the moment arm of this resultant force from the triangular distribution. But then also, the other force, F2, from the uniform distribution will also cause a negative moment at position L over 2, right? The only thing that offsets this and prevents the beam from beginning to rotate clockwise is the fact that out at L, force B is upward, right? In other words, there's a reaction force here at B and a reaction force at A. The reason that A doesn't appear in the equation, of course, is because A has a zero moment arm. It passes through point A, and therefore, technically it's in the equation, it just has a zero moment arm. Okay, so from this equation, we can solve for B. Now notice one thing that happened really nice by using symbols, notice that the length L canceled through the whole equation. You might not have noticed that had you plugged in 8, especially if you'd taken 8/3 and plugged it in as 2.66, right? You wouldn't notice that that length cancels. So if we take these other two terms to the opposite side of the equation, at least what's left, we have F1 over 3 plus F2 over 2. Now, of course, we know the magnitudes of these two forces, so F1 and F2 are actually the same. So we could simply pull it out and call it F. But I'm going to plug in the number as well. All we need to do is add 1/3 to 1/2, and we will have B, the load B. In fact, it comes out, once you plug this into your calculator, it comes out to 33.3 repeating kilonewtons. And so that's the reaction at B that we were asked to find. Now, how would we calculate the reaction at A? Well, you could sum forces in the vertical direction to calculate A. In fact, you should do that, but I'd like to check my work and make sure that I haven't made some dumb mistake along the way. So what I would do is go ahead and sum moments about point B as well as follows. So summing moments about point B, counterclockwise positive. Well, I hope we get 0, right? That's our goal because we're in statics. So summing moments about point B, well, that's over here, and now F1 and F2 have a positive moment arm, whereas the reaction at A will have a negative moment. So writing this out quickly, we've got F1, we've got to be careful, we're summing moments about point B, and the length out to where F1 acts is 2/3 the length. Before it was 1/3 because we were measuring from A, now we're measuring from B, so it's 2/3 of the length. That's the moment arm for F1. F2's moment arm is still L over 2, just like it was before, because the distance between B and the point and A and that point where F2 is applied is exactly the same. But then finally, the vertical component at A, which that's all there would be, so the reaction force at A is causing a negative moment about point B, and it has moment arm, of course, L. Since we're in statics, that all comes out to 0. The thing's not beginning to accelerate angularly, right? So, rearranging this just a bit, again, by the way, the length cancels out. We'd have A, the reaction A equals F1 2/3 plus F2 times 1/2. Of course, F1 and F2 are the same thing. They're both 40 kilonewtons still, so we simply need to add 2/3 to 1/2 in order to come up with the reaction at A, and then of course multiply by 40. When you do that, you find that the reaction at A is 46.6 repeating kilonewtons. And so those are our two answers, but now we've got a nice check built in. because we know that the sum of forces in the vertical direction, of course we're assuming regular, x, y coordinate system like we always use, sum of forces in the vertical direction has to come out to 0. Well, that's a negative 40 kilonewtons minus 40 kilonewtons, right? Because we've got two resultant or equivalent loads acting downward, and then we've got reactions acting upward. So that would be plus 46.6 repeating plus, and I'm dropping my units, so why don't we just drop it throughout? They're all going to be kilonewtons, so we're fine. So plus 33.3 repeating, and of course this comes out to 0. Do the math, it's easy. That's just 80, and that's negative 80, and so they cancel out. So that's a nice check to verify that yes, in fact, we've worked the problem properly, and those are the results of the problem, or in other words, the reactions at A and B. So now, moving on to problem 3. The boom of a crane has a weight of 3,000 pounds and center of gravity at G2. It is supporting 1,500 pounds of pipes. Theta, the angle of the boom from the horizontal is 30 degrees. Assume the cables at the top of the boom are rigidly attached. The crane body weighs 8,000 pounds, has center of gravity at G1. Draw a free body diagram of the crane showing all the forces and reactions acting upon it. Then solve for the values of the reactions at A and B. Now, some of you made the mistake of trying to take this problem and make a free body diagram that basically didn't include part of the B. What you were thinking was that, we've got the weight of the boom acting down here, we've got the weight of the payload acting here, we've got, the weight of the crane acting somewhere here, there are reactions at A and B, and you got kind of confused because you thought, well, then I shouldn't do that. I should make a, let's see, how would that really look? It's actually over a little bit, something like this. So let's put it there, there we go. And we'll do something similar for A, something like this. It really doesn't matter. But you got confused because you tried to include the force from the cable that supported the beam. If you want to do that, that's fine, but take the beam as a free body, right? So take this beam and think about it this way rather than the entire crane. Notice we don't care about the beam independently. What we care about are the reactions of the ground. So why not take the whole thing? Because think about it, there also must be some equal and opposite force. Since these two are equal and opposite forces in the same body, they are internal forces and they don't matter. We're not interested in the cable tension at the top of the boom. We're interested in the reactions to the ground. So you simply take the whole thing as a free body. Okay? So anyway, we know this is point G1. Let's see, where is G2? It's over here. And we also know the magnitudes of these weights. Why don't we just jot them down? Weight of the crane, I think that was 8,000 pounds. Yeah. The weight of the boom was not insignificant. It was 3,000 pounds and all of that to move a payload around that was 1,500 pounds. But again, the load from that upper cable is internal to the free body that we're interested in. So here's a proper free body diagram of the crane and its loads and so forth. So what I did is I decided to sum moments about point A taking counterclockwise as positive. So over here, or here, if you will, anywhere along this line is fine. I'm going to sum moments about that point, or, you think of it down here. All that matters is the horizontal distance to things. That's all that really matters when we're summing moments about point A. Why the horizontal distance? Because all the forces we are dealing with are purely vertical. So all we need is pure horizontal moment arms for each. Anyway, to keep myself straight, I went ahead and wrote 0 because all these moments had better come out to 0. And, well, let's see. A passes through the point, so it doesn't provide a moment. The weight of the crane does not, and it causes a negative moment, so I wrote -4 feet. And you know what, I'm going to drop the 4, or the feet off of it, because I don't have a whole lot of room here. But basically I'm looking at that distance as the moment arm for the 8,000 pound force. So then to keep everything straight, I just put symbols in, weight of the crane. Now the reason I did all of this is because For one thing, I've got a lot to write. Also, the geometry is a little bit complicated, and some of you messed up on that because the point of attachment between the crane and the boom is actually, despite my scale here, which is pretty bad, 3 feet over from the point of contact between the one of the treads and the ground. Now, in reality, obviously the tread is fairly wide. We're just assuming that the reaction from the ground acts at the center of that tread. That's what we've been given here, so it seems reasonable to use that. But then there's a further 6 feet between G1 and this point of attachment of the crane. So you got to be really careful here. Because if you're interested in the moment arm for the weight of the boom, for example, you don't want to count these 3 feet, right? You need to go over from A by 10 feet and add to it, well, I gave you dimensions like 12 feet here, and from that point on 15 feet out to the payload. Okay. So we want just the horizontal distance. Well, if we know the angle theta is 30 degrees, then we can look at this as a right triangle and figure out what that distance is. So basically what we need is 4 plus 6, which is 10, plus this distance, which is 12 times cosine of theta. And I just write c theta for cosine of theta, okay? So we've got to get that right. Don't be confused by these 3 feet. We're not to that point yet, right? I'm trying to take care of the, I guess I should add the weight in, shouldn't I? Now that I've calculated the moment. I'm just trying to figure out the moment of the weight of the boom. And so I need 10 feet plus 12 cos theta, okay? Now, obviously this causes a negative moment. That's why I had a negative sign there. I'm going to go ahead and break the line and just continue on the next line so I'll have enough space. But then I need to take the moment of the payload as well, and I'll put the moment of the reaction B last, okay? But for now, let's just continue out along the boom, because it's actually going to look a lot like this. It's a negative moment, and we've got to add 10 feet to get us from here to here. And then we need the cosine of theta times the sum of 12 and 15. Well, 12 and 15 are 27. So we need plus 27 feet cos theta to get the horizontal moment arm from here to here, right? And that needs to be multiplied by the weight of the payload. But then what offsets all of this is plus, now let's see, 10 feet plus 3 feet to get out to B is 13 feet, and then times B. Well, I guess I already wrote equals 0. So that's it. That's our equation. That's our sum of moments equation about point A. Now, since we know the weight of the crane, the weight of the boom, and the weight of the payload, and this all comes out to 0, we can calculate the reaction at B. So B is equal to, well, let me just move these down. So basically, I'm going to put all these terms that are negative on the other side of the equation, and at the last step, I'll divide by 13, right? So we'll put these on the other side, so that means it becomes positive. It's 4 times the weight of the crane. The weight of the crane is 8,000 pounds. Again, I'm skipping my units, but it's foot-pounds divided by feet, so we'll end up with pounds for B. And then plus 10 plus 12 quantity cosine 30 degrees times the weight of the boom. The weight of the boom was 3,000 pounds. And then finally, the payload had moment arm 10 plus 27 cosine 30 degrees multiplied by 1,500, and I'm probably off the screen just a bit in the camera, but you get the idea. All I've done is I've moved these 3 terms to the other side and then divided by the multiplier on B. And of course, determined that the unit should be pounds. When you plug all this into your calculator, you find that the reaction at B is 11,019 or so pounds force. So there's the reaction on this tread down here. I hope it can take that load, because that's what it has to support. And of course, the reason for using a track like this is to take that load and spread it out over the ground. You put a load like that in a concentrated area on just dirt or gravel, and it'll sink right in. Can't do that. That's what treads do for you. In fact, often treads have a lower pound per square foot loading than a tire, like a road tire. Anyway, I decided, instead of summing moments to find A, that I would go ahead and simply sum forces in the vertical direction. So I wrote A plus B, in other words, the reaction at A and B minus the weight of the crane, minus the weight of the boom, minus the weight of the payload must come up to 0. And so that allows me to calculate the one unknown, which is A. Notice we just calculated B. We know the weight of the crane, the weight of the boom, and the weight of the payload. So we just have to rearrange and say A is equal to, well, the weight of the crane plus the weight of the boom plus the weight of the payload minus whatever B is supporting, right? B is supporting part of this. It's like A and B are working together. In fact, that's exactly what it is, to support these three weights. So if you plug in all the numbers, it's all known. I'll plug it in for the sake of completeness. The crane's 8 grand, or 8 kips, I should say. The weight of the boom is 3 kips. Kips, by the way, are just kilopounds. I'm writing in pounds, really. So anyway, the weight of the payload is 1,500, and then we calculated the support from B. If you plug all these into your calculator, you'll find that A is only supporting 1,481 or so pounds. And that's the reaction. Now, I did go ahead and calculate the moment just to verify that I had done everything correctly. So I went ahead and summed moments about point B, taking counterclockwise as positive, and said, well, let's see. The moment of A is the force at A times the moment arm, which is a 13-foot moment arm, right? 10 plus 3 is 13. So A is acting to cause a clockwise moment about B. I'm summing moments over here now. And so it's a negative A times 13, right? Of course, I'm going to plug in numbers, I guess, because we're verifying. So 1,481 pounds multiplied by 13 feet. Of course, all of these are feet and pounds now, so I'm not worried about the units coming out wrong. They should be fine. And then if I'm summing moments about B, I need to take the moment of the weight of the crane. Well, that's a positive moment, and it's a 3 plus 6 or 9-foot moment arm. Let's be consistent and use the loads first, or write the loads first, and then the moment arm second. So a 9-foot moment arm for that 8,000-pound load. Now, if we're summing moments about point B, then the weight of the boom is actually going to have a positive moment arm, so will the weight of the payload, right? Or I'm sorry, it'll be negative, excuse me. So A was negative, the weight of the crane is positive, but these two will be negative. So they're a little more complicated in terms of their geometry. So let me do this. Let me move to the next line. So the boom is going to cause a negative moment about point B. But notice if I take 12 times cosine of theta, I'm going to get the length from B all the way back to this point. So I've got to subtract 3 feet from it. So what I'm going to do is say 12 cos theta, or cos 30 degrees, minus the 3-foot moment arm. So I actually just get the distance from B over to the point where the weight of the boom is applied. And then, of course, I need to multiply by the 3,000-pound load. I guess I should put that first, but that's good enough. We got the moment arm first, load second, that's fine. And then the next one is the weight of the payload. Now, it has 27 cos 30 degrees minus 3 for its moment arm from here to here. Understand, I've calculated the entire length from here to here and then subtracted off the 3 feet, just like I did before, times 1,500 pounds. And I think that's it, right? We've got the moment, summing moments up out here. There should be 1, 2, 3, 4 terms. 1, 2, 3, 4. Yep, that's it. This should come out to 0. The question is, does it? Well, if you plug it into your calculators with the round off that I've used, it does come out close enough to 0. Okay? That's not exactly 0 because, of course, I've rounded off these two numbers. And, of course, this number appears in the equation, but it's close enough. It's within the margin of error for the precision of the calculations I'm using because of the way that I rounded off. So let's move on to the last problem. This is the one where people struggled the most. At one stage in the assembly of a bicycle, the following couples and force are applied at the points indicated. Determine the equivalent force couple system at O and the resultant moments mx, my, mz. Here was the key equation that most students missed. All of the moments at some point O, for example, is equal to the sum of all the moments that are applied, I'm using the bar to indicate a vector, plus the moment of all the forces applied. Okay? So basically, all you had to do to solve this problem was add up moment A, moment B that I gave you, and moment C, and then you had to take the moment of the force that was applied at D. That's all you had to do. So you had to calculate, you had to know how to write the position vector from O to D, take the cross product of that position vector with the force that was applied at D, and this is simply the moment of that force. It gets added to the others, and that's it. That's how you calculate all the moments. Now, a lot of you tried to apply that moment to a particular point, or you tried to use the point information. I purposely gave you point information. I wasn't trying to trick you per se, but I did want to see, did you know that it doesn't matter where you apply a moment to a rigid body, you will get the same effect on the body. And so that's why, you know, we do reference this to point O, but that's just because, it's not because of this term, it's not because of these moments, it's because we need to know the moment of the force about that point. You see, the moment of this force will depend on what point you're taking the moment about, right? If you take the moment of this force through D, that force will have no moment. And so that's why this moment is referenced to a particular point. It's because the force gives rise to a particular moment, okay? So anyway, this is what you had to do. So the first three are pretty simple because you only got single components. For the moment at A, for example, it was negative 30 kbar. The moment at B was negative 35 kbar, and they're all the same units. They're just foot-pounds, so I won't bother writing down the units. And then the moment at C had two components, negative 10I minus 25J. So this bit here came from the moment at C. We don't care about the point. We don't need the point where these things are applied. It's fine. Now, I did ask for the force couple system. Right now, we're only working on the couple part. We're working on the moment part. We'll work on the force here in just a second. That's actually really easy. But we have to somehow take the cross product of R and F. So we have to write down the vector R from O to D. So let's do that. O is at the contact point of the front tire. D is up on the seat post, it looks like. And fortunately, I gave you position coordinates for the moment and for the force in terms of point O. So actually, when I told you that the force at point D is equal to negative 15I minus 40J, and then I said at D, which was 2.5I plus 3J plus 0K, so you don't really even have to write that part. This is the vector. Because this is a position vector that goes from O to D, right? Now, of course, I gave you this in just X, Y, Z coordinates. But all you had to do is pick off the various coordinates and put them with the correct unit vector. So that's the position vector from O to D. Now all we have to do is take the cross product of these two vectors, right? That's what this says to do. Just take the cross product. So how do we do that? Well, the easy way is to take the determinant of this matrix as follows. We need R first, 2.530, and F, negative 15I minus 40J and 0K. So this will be a very simple cross product because when we take the cross product for I, it'll just be 0, right? Because we're going to take, 3 times 0 minus 40 times 0, that's 0. For J, we take 2.5 times 0, negative 1.5 times 0, that's 0. So the only time we're going to get a result is when we take the K cross product, right? And remember, it's positive, negative, positive, so this will end up being positive, or at least we don't have to attach a negative sign in front of it like we do with J. So we need 2.5 times negative 40. Let me move that K out of the way temporarily. And from that, we have to subtract 3 times negative 1.5. And of course, multiply all this by the unit vector K. Sorry if it's off the screen. And that's it. So let's see. Let me make sure I got my information right. Yeah. So if we take, I guess I'll have to do this in my head because I used a calculator here. Anyway, so 2.5 times 40 would be what, 100? And then negative of negative is positive, so, but I'm thinking I should come up with, no. Oh, I know what's wrong. I wrote 15 here, and here I wrote 1.5. I'm sorry. This should be 15. So 3 15s are 45, so this is 145K. And it's a positive, right? It's in the positive K direction because the number comes out positive. So that is the cross product. This cross product is nothing more than 145K. That's it. So we have to tack that on to the end of this equation. Let's put it in here. So plus 145K. All right. Now where's the other K components? Well, there's two of them right here. So we can write, let's put it in proper order, ijk, negative 10I minus 25j. And let's see, this is what? Negative 65. We have here plus 145. Let's see. And I may have gotten the wrong, what have I done wrong here? I did do, oh, yeah, I forgot my negative sign. So 2.5 times negative 40 would be negative 100. That's my fault. So negative 100 plus 45 would give us negative 55. That's better. Pardon me. So that was actually the cross product, negative 55K, assuming I've done the math right at this point. So we've got negative 55 plus negative 30 plus negative 35, going to come out negative obviously, and that's negative 120K. Now the units for this vector are foot-pounds. How so? Well, I gave you foot-pounds for these moments, right? What about this? Well, R is measured in feet, and F is measured in pounds force. When you take the cross product, it's kind of like multiplication, and so it's just foot. In fact, we multiply the scalar components themselves. So we simply get feet-pounds or foot-pounds for the cross product, and then we have consistent units. So this is the sum of moments on it, or the equivalent moment. And this moment could be applied at O and have the same exact effect that MA, MB, MC, and the moment of that force have on this bicycle. It would be identical, assuming the bicycle is rigid, right? But what about forces? What would be an equivalent force? In other words, if I want to apply a force at O, how much force would I apply? Well, here's the mind-bending part of it to me. We can move the moment vector anywhere we want. We can move the force anywhere we want. And notice the only force applied is this. So it's simply negative 15I minus 40j. And of course, these are pounds. So you put this moment and this force at O on the bicycle, and if the bicycle is rigid, this force and moment system, this force couple system, will have the exact same effect on the body that these three separate moments plus the force has on the body, because the force has a moment about O. So this is an equivalent force couple system to what we were given. Now, students are confused a little bit about the difference between an equivalent system and a sum of forces. We're not saying here that we're trying to say sum of forces equals 0 and sum of moments equals 0. We're just trying to say this is not what we're doing. Right? We're not trying to find some reactions so that we have a static situation. We're just trying to find an equivalent force and moment we can apply at O to have the same effect on the body, or an equivalent effect to the moment and, or the three moments and the moment of the force that is applied to the seat post. Okay? So that's it. That's how you work this problem. I think one thing that may have confused students a bit is the fact that I gave you the moment at C as a double-headed arrow. What I was trying to do there was point out that this moment has some I and J components. Okay? I couldn't really draw a circular arrow that was coming out of the plane, right? That wouldn't work. So I had to use a double-headed arrow. Whereas for the moment at A and B, those have a pure K component. Of course, they're both negative. They're both into the page. But you could imagine a double-headed arrow going into the page at A and B, representing the moments at A and B respectively. So that's it. So don't be confused about summing forces and summing moments to figure out reacting or reaction forces and moments versus an equivalent force moment system to what we were given.